Right now, in a lab somewhere on this planet, a machine is sitting idle with 1.5 terabytes of memory installed inside it. And nobody in that room is thinking about spreadsheets or databases. Because the only question anyone actually cares about is how many browser tabs it takes to bring a computer this powerful to its knees. And this time, the experiment has a twist. Nobody has tried at this scale before because instead of torturing a single operating system until it collapses, the exact same punishment gets run twice, back to back, on the exact same hardware, once on Windows and once on Linux. And the gap between the two results is going to change how you think about every computer you have ever owned. Before a single tab opens, you need to understand the machine itself, because this is not a gaming rig with a flashy paint job. This is two AMD EPYC server processors bolted into one motherboard, 96 cores apiece, 192 physical cores combined, and once hyper-threading kicks in, the operating system is juggling something close to 384 logical threads at once, all of it feeding off 1.5 terabytes of DDR5 memory, which is not a typo. That is more memory than most people will interact with across their entire lives. Combined, stacked into a single chassis that looks less like a computer and more like something you would find quietly humming away in a data center processing financial transactions or running climate models, not opening YouTube in 4,000 separate windows. This exact stunt has a history, and it matters. Because a few years back, a well-known reviewer took a workstation loaded with almost identical memory and pushed Chrome until it physically could not open another tab. And the machine cracked past 6,000 tabs before one of the browser's own background processes seized up, and I dragged the whole thing down. And that result has been sitting in the back of every hardware nerd's mind ever since, because it left one obvious question completely unanswered. What happens when you hold the hardware constant and swap out the operating system underneath it? And that is exactly the gap this new test was built to close, taking that same brutal automated tab flood and running it identically on Windows 11 and on a Linux distribution on the same dual processor monster, to see which one actually keeps its composure when pushed past every reasonable limit a computer is supposed to have. Here's the part almost nobody explains properly, and it is the reason this test is actually interesting instead of just a big number on a screen, because modern Chrome does not treat a tab as some lightweight little document floating inside one shared window. Every single tab spins up as its own separate process, with its own slice of memory, its own security sandbox, its own private connection back into the browser's rendering engine, and that architecture exists on purpose. Because if one tab crashes from a broken website or a memory leak, it dies alone instead of taking your entire browser down with it, but the price for that safety net is overhead, real overhead, paid on every single tab before it has even finished loading a single pixel. And that cost compounds relentlessly the moment you start, counting tabs in the thousands instead of the tens, which is exactly why raw memory capacity alone was never going to be the whole story here. Long before the system technically runs out of memory, something else usually gives first, because every one of those thousands of processes is fighting for a slice of CPU scheduling time. Everyone is holding open its own network connection. Everyone is keeping file handles and system resources alive simultaneously. And this is precisely where the operating system itself stops being a background detail and becomes the entire story. Because Windows and Linux do not manage memory scheduling and resource allocation the same way, not even close. And the difference comes down to decades of completely different design priorities. Windows built from the ground up around massive hardware compatibility and a smooth desktop experience for a billion ordinary users. And Linux, especially in its server configurations, refined for decades around exactly this kind of brutal, sustained, resource-starved workload, with a kernel that hands administrators a level of granular control over memory and scheduling that Windows simply was never designed to expose. And here is where it gets genuinely dramatic, because Linux carries something called an out-of-memory killer buried inside its kernel. A mechanism built specifically for the moment a system is about to run out of memory entirely. And instead of letting the whole machine seize up into an unresponsive frozen mess, that mechanism steps in and surgically kills off whichever process is hogging the most memory, sacrificing one process to save the entire system, while Windows historically has never had a true equivalent working in quite the same aggressive automated way, which means a Windows machine pushed to its absolute ceiling can behave completely differently, under that exact same pressure, sometimes sliding into a slow, sluggish, system-wide freeze instead of Linux's more surgical one-process execution. Then, there's a second, quieter architectural difference that almost nobody outside of server administration ever thinks about, something called non-uniform memory access. And on a dual processor system exactly like this one, it becomes enormously important because each processor has its own physical bank of memory directly attached to it, and accessing memory sitting right next to your own. processor is meaningfully faster than reaching across the system board to grab memory attached to the other one, and how gracefully an operating system handles that distinction can make or break performance once you scale a workload up to something this extreme, with Linux historically giving administrators direct hands on control over that behavior through kernel-level tools, while Windows tends to handle it automatically behind the scenes with far less manual control handed to the user, and on a test specifically. Engineered to hammer memory allocation across 192 physical cores, that architectural gap stops being a trivia footnote and becomes one of the single biggest hidden variables separating how each operating system actually holds up. Obviously, nobody's opening 4,000 tabs by hand, so a test like this runs on pure automation, a script instructing the browser to open a fresh tab, load a real page, wait for it to finish rendering, and immediately repeat the cycle again and again for as long as the test demands, which keeps the whole process consistent and repeatable and lets the results be genuinely compared side by side instead of being polluted by human error. And it is worth pointing out that these are not blank placeholder tabs either, because a blank tab point collapses unless every single tab is loading a real, fully rendered, image-heavy, script-heavy modern web page, the kind that is dramatically more demanding today than it was even 5 years ago, because that is the only way the test actually measures anything close to real-world browsing behavior, instead of just an empty number. And here is the twist that catches almost everyone off guard the first time they hear it, because in the earlier version of this experiment, the machine still had memory left in the tank, real headroom, when the browser itself started to visibly buckle, individual processes freezing up and becoming unresponsive long before the memory pool was anywhere close to exhausted. And that same pattern shows up again and again across nearly every version of this test, regardless of which hardware or operating system gets thrown at it, because the browser itself, not the operating system underneath it, is usually the first thing to actually break. The sheer number of simultaneous connections and background tasks overwhelming Chrome's own internal architecture long before the operating system's memory management genuinely runs dry. This is not just a fun stunt either, because server administrators and cloud infrastructure engineers deal with exactly this kind of underlying operating system behavior every single day of their working lives, just without the entertaining framing of a browser. Tab stress test wrapped around it, and choosing between Windows Server and a Linux distribution for a genuinely memory-hungry production workload is a real, expensive, consequential decision companies make constantly, which means a test like this one, however playful its presentation, actually surfaces real measurable differences in exactly the way each system behaves once memory allocation and process scheduling get pushed to a genuine extreme, and a browser cracking open thousands of tabs is really just a fun, visually intuitive stand-in for the exact same underlying stress a database cluster or scientific computing pipeline might face during a sudden, enormous spike in simultaneous demand. There is a real economic story hiding inside this hardware too, because dual processor server systems, with this kind of core count and memory capacity, are not niche toys built purely to entertain an audience. They are real commercially deployed configurations that companies actually purchase for exactly this kind of memory. Intensive, highly parallel workload, in-memory databases, massive virtualization platforms hosting hundreds of separate virtual machines at once, and increasingly the artificial intelligence and machine learning infrastructure that demands enormous, fast, low-latency memory pools. And a build like this one, easily running into 6 figures. Once you account for the dual server-grade processors, the specialized motherboard, 1.5 terabytes of server-grade memory at current pricing, and the power and cooling infrastructure needed to keep it running reliably, sits firmly in genuine enterprise territory, nowhere near even the most extreme consumer setup you could imagine. It is also worth understanding the specific silicon choice here, because the processor selected for this build is built around a manufacturing technique that stacks additional cache memory directly on top of the processor die itself, dramatically expanding the pool of extremely fast, low-latency memory the chip can lean on before ever reaching out to the comparatively slower main memory pool, and that matters enormously for a workload, juggling thousands of simultaneous browser processes, because keeping frequently used data sitting close in ultra-fast cache instead of constantly reaching across the system for it is exactly the kind of advantage that decides how far a test like this can actually go before something finally gives, which strongly suggests this specific hardware was never a random pick. It was almost certainly chosen because its architecture is unusually well suited to precisely this kind of massively parallel, cache-sensitive punishment. Think for a second about everything that has to work correctly at the same time just to make an experiment like this possible at all. An operating system, capable of tracking and scheduling potentially thousands of separate processes without the scheduling system itself collapsing under its own overhead. a network stack capable of handling thousands of simultaneous outbound connections without slamming into router or firewall limits that have nothing to do with the computer's raw hardware at all. Storage fast enough to absorb the constant background disk activity browsers generate, even while running mostly in memory, because browsers are always quietly writing cache files and session data even during completely ordinary use. And any single one of those secondary systems becoming the bottleneck could artificially cap the entire test result long before the actual memory pool ever gets close to running dry. Which is exactly why a test like this tends to reveal so much more about total system architecture than any single specification on a spec sheet ever could. There is a specific, almost invisible limit worth understanding too, because operating systems cap how many files, network connections, and other resources a single process or the entire system can hold open at once, and every tab opening a network connection eats one of those slots, with every image and script and embedded element on the page potentially consuming several more. And Linux server configurations typically ship with these ceilings set far more generously than a default desktop system, with administrators able to raise them directly through simple configuration files, while Windows manages the same underlying concept through an entirely different mechanism. And even though modern Windows has raised these ceilings dramatically compared to years past, the two systems still approach the exact same underlying problem from fundamentally different philosophies. And a test slamming thousands of tabs into the system simultaneously, each one spawning multiple connections of its own, is precisely the scenario where these normally invisible limits can suddenly become the deciding factor in how far the whole experiment manages to go. Chrome itself is not just sitting there passively taking the punishment either, because the browser actively fights back against exactly this kind of runaway resource explosion through a feature that automatically identifies tabs you have not touched recently and quietly, unloads their content out of active memory, keeping just enough information saved to reload the page instantly if you ever switch back, and under ordinary circumstances that feature is genuinely useful, preventing exactly the kind of memory explosion this test is deliberately trying to trigger on purpose, which means anyone running a serious version of this experiment has to carefully account for that self-preservation behavior, because a naive test might technically open thousands of tabs, while the browser quietly deactivates most of them behind the scenes, completely undermining the entire point of the exercise and producing a number that looks impressive but measures almost nothing real. Stepping back from the raw numbers for a second, there's something almost poetic about watching a machine this absurdly overbuilt get pushed past its limits because the entire premise taps into something universally relatable. The quiet frustration of watching your own browser slow to a crawl with what is probably a genuinely modest number of tabs open, somewhere between 10 and 30 for most ordinary people. And the honest truth buried underneath all of this is that even a machine boasting 192 physical cores and a full terabyte and a half of memory still eventually finds its own breaking point, just at a scale almost nobody watching this will ever personally need to worry about, because the underlying architecture, the process overhead, the scheduling complexity, all of it scales proportionally, which means your own completely unremarkable laptop is fighting the exact same fundamental battle this monstrous server is fighting, just at a dramatically smaller and far more relatable scale. And that is really the entire point of running an experiment this extreme in the first place, because pushing a system this far past any realistic real-world use case is precisely how you expose the architectural differences that stay comfortably hidden during ordinary everyday computing, differences that only ever surface once you drag a machine kicking and screaming toward its absolute limit. And once you understand what actually broke first here and why, you'll never look at a sluggish browser or a frozen laptop quite the same way again.